Hello and welcome to section 1 of module 1, the big picture. In this section we will be answering the question, what is neurotechnology? We've broken up neurotechnology into 3 categories. Number 1 is neuroimaging, number 2 is neuromodulation or neurostimulation, and number 3 is brain-computer interfaces. Some technologies belong in more than one of these categories, some technologies don't belong in any of these categories, but we think this is a good place to start. So, a good way of thinking about these categories is that neuroimaging is a way to understand the brain. Neuromodulation and neurostimulation are ways to do stuff to the brain, and brain-computer interfaces can be used to do stuff with the brain. Neuroimaging was a pivotal moment in the advancement of neurotechnology because it allowed scientists to monitor the brain's activity while performing experiments. Understanding the brain is obviously the bedrock of building neurotechnologies that can do stuff to the brain and with the brain. Without understanding the brain, we can't build neurotechnology. So in this lesson, we'll be addressing 2 types of neuroimaging. Number 1 is electrophysiological neuroimaging. In this type of neuroimaging, you are directly measuring electrical activity of neurons. The 2 big examples, electroencephalography, or EEG, and magnetoencephalography, or MEG. With EEG, you're recording the brain's electrical activity, and with MEG, you're recording the magnetic fields produced by the brain's electrical activity. In later sections and lessons, we'll go much deeper into how these techniques work. Both EEG and MEG are non-invasive, which means no surgery is required to perform them. The other type of neuroimaging is metabolic neuroimaging. In this type of neuroimaging, you are not directly measuring the brain's electrical activity, but rather indirect measures or consequences of the brain's electrical activity. Examples of these consequences include blood oxygenation levels and emissions of radioactive chemicals in the bloodstream. A good analogy to think about metabolic neuroimaging is a thermometer. A thermometer doesn't directly measure temperature, but rather the volume of mercury in a glass tube. The volume of the mercury increasing is a consequence of the temperature rising, just like how blood oxygenation levels are a consequence of the brain's electrical activity. There are 3 main types of metabolic neuroimaging. Number 1 is fMRI, functional magnetic resonance imaging. Number 2 is positron emission tomography, or PET. And lastly, we have functional near-infrared spectroscopy, or FNIRS. Each of these techniques are measuring an indirect consequence of the brain's electrical activity. So, fMRI is measuring blood oxygenation levels, PET is measuring radioactive emissions of chemicals in the bloodstream, and FNIRS is measuring absorption of infrared light by hemoglobin. There is a key distinction to make between electrophysiological neuroimaging techniques and metabolic neuroimaging techniques, and that is their temporal and spatial resolutions. Temporal resolution is the precision of measurements in relation to time, and spatial resolution is the precision of measurements in relation to space. So what does that mean? A high temporal resolution means your measurements are not delayed, and a high spatial resolution means that your measurements are very close to where they actually occurred. Electrophysiological neuroimaging techniques have high temporal resolution and low spatial resolution. So this is EEG and MEG. Don't be confused by the positions of the circles on the graph. High temporal resolution is good, and it's equated with a low temporal resolution number. That's because high temporal resolution means your measurements are not delayed, so the number itself is very small. For electrophysiological neuroimaging, it's on the scale of milliseconds. However, electrophysiological neuroimaging techniques have low spatial resolution. That's because electrodes are placed on the scalp, which means it's difficult to pinpoint exactly where the electrical activity is coming from. Each electrode placed on the scalp is recording the sum of electric fields for hundreds and thousands of neurons. However, on the bright side, we have high temporal resolution because we are directly recording neuronal activity. On the other hand, metabolic neuroimaging, we have low temporal resolution but high spatial resolution. Why do we have low temporal resolution? That's because we are measuring an indirect consequence of the neuronal activity, not the activity itself. So there's a time delay. For example, with fMRI, it takes a few seconds for the blood oxygenation levels to rise. There's a significant delay between the brain activity occurring and the blood oxygenation levels rising. As you can see, there are benefits to both electrophysiological neuroimaging and metabolic neuroimaging. That's why you'll often see that these two techniques are used in conjunction. Electrophysiological neuroimaging is useful for its high temporal resolution, which means there's little delay in measurements. On the other hand, metabolic neuroimaging techniques are often used for their high spatial resolution, because you can often pinpoint where the brain activity is coming from. So in summary, the first category of neurotechnology is neuroimaging. This includes electrophysiological neuroimaging and metabolic neuroimaging. Electrophysiological techniques have low spatial resolution and high temporal resolution. That's because they are measuring the brain activity directly, but at the same time, electrodes are placed on the scalp and it's hard to pinpoint where the activity is coming from. On the other hand, metabolic techniques have high spatial resolution but low temporal resolution. In the next lesson, we'll be covering the second category of neurotechnology, neuromodulation and neurostimulation.